Hello again. We're continuing the same lecture handout. We're on valence bond theory. We will do valence bond theory and pi sigma bonds. And the rest of the lecture, which is molecular polarity and intermolecular forces, will be examined the week after. So next week, this week we're doing valence bond theory, and then next week we're doing molecular polarity and intermolecular forces. So let's begin right away. This is an abstract topic. What do I mean by this? This topic is an application of quantum mechanics. It's an extremely important topic because it explains to us the nature of bonding in terms of quantum mechanics. So far, we have been talking about bonding occurring to lower the energy of the system, but we did that by talking about energy, talking about the nuclear forces. The nucleus is attracted to the electrons, and thus that lowers the energy. But still, we didn't talk about quantum mechanics, meaning the orbitals and the shapes of those orbitals, the S and the P. So this is the chance to talk about it. So let's start. So Lewis structures and Vesiper do not explain why a bond forms. They do not. So Vesiper, remember, that was molecular geometry. Okay, that's what Vesiper is. Valence shell electron pair repulsion model. So how do we account for the shape in terms of quantum mechanics? Orbitals, energy levels, all of that stuff. What are the orbitals that are involved in bonding? And for that, we use a very important theory. It's called valence bond theory. So valence has to do, again, with the outer shell. And of course, bonding is, again, the sharing of a pair of electrons, or more in terms of double and triple bonding. So it says bonds form when orbitals on atoms overlap. And there are two electrons of opposite spins in the orbital overlap. Here it is. If you remember, for H, we have hydrogen and hydrogen. If you remember, for H, we have a 1s1 and a 1s1. Oops. That was the electron configuration. So here is the S. I'm going to use this color. Okay. So here's our S. And S. These are those orbitals. And there are, of course, electrons in those, one electron each in the orbitals. That's what the valence electron is for hydrogen. And if you notice that when they get near each other, there's an orbital overlap region. It's darker right there. It is darker in the middle. And that's basically where the bond, or the majority of the bonding, occurs. We can look at the H and Cl when you form HCl. Well, this is the 1s for the H, and the 3p because that's the valence orbital for the chlorine. It's 1s2. Remember, it ends with, so I'm just going to jump to the end. If you check your, it would be neon 3s2, 3p5. So here's our 3p. So the 3p is this one right here is overlapping with the 1s on H. And that's again where the bonding occurring. This is Cl and a Cl. This is Cl2. Same thing. You have the 3p and the 3p. So again, that is valence bond theory trying to explain. But these are very simple examples. I mean, we can just say, okay, we have an unpaired electron in the S and in the P, and then they merge together. But we have to expand this when we get to more complicated structures, like we have more bonds. Let's say if we have 4 bonds, 5 bonds, even 3 bonds. Here, all we have is a 1 bond structure. So that's where the topic of hybridization comes from. It says in polyatomic molecules, the formation of electron pair bonds and geometries of molecules must be explained in terms, as we said, of quantum mechanics. You have to use quantum mechanics. Otherwise, what we have learned was a waste of time. Atomic orbitals on an atom mix to form new orbitals called hybrid orbitals. So we're going to show you in a second, but the idea of hybrid means you're mixing 2 different things and you get a product that is a mixture of both, right? So hybrid orbitals have different shapes than original atomic orbitals, and they hybridize as they approach each other. And the most important thing is you have to remember this, is that the number of hybrid orbitals on atoms equal the number of atomic orbitals mixed. So let me give you an example. So before we show you this sp2, sp3, all of that stuff. So say we have an S, and we mix this with the p orbitals. You're aware that there are 3 p orbitals. Okay, I drew this because, so this is px, this is py, and this is pz. If you recall, orbitals, the p orbitals, we have 3 of them, and they're along the 3-dimensional axes. If you mix them together, if you take the S and mix all of them together, you get what we call hybrid orbitals. So those right here okay, so those right here are called atomic orbitals. They're atomic orbitals. When you mix them, you get hybrid orbitals. And the hybrid orbitals is if you mixed 4 right here, these are 4 orbitals, you would get 4 orbitals out, and they would look like this. Large lobe, small lobe, large lobe, small lobe, large lobe, small lobe, and of course, the last one would look like this. So you have 3 orbitals right here, and 4 I mean, and those are now called sp3 orbitals because it's s and 3 p's. Okay, of course it's abstract, but that's actually the idea of the geometries. The geometries do not come from bonding. They actually come because of those hybrid orbitals. So let's look down here. Here's methane. Methane is CH4. We've seen the structure of methane, and it's a tetrahedral. Tetrahedral. So a tetrahedral has the four faces, and you have CH4. So imagine here's carbon. So carbon has these hybrid orbitals. It has the four of them, the ones I drew. I tried to draw them as best as I can. Here's this one. This one right here is that one. This one is down here. And then this one is in the back, and this one is on the top. The best of your ability. Of course, there are better pictures. When you add the four hydrogens, so what happens is now the hydrogens are in the s orbitals. And look at the overlap that is happening. You have an overlap right here, okay? And these, of course, we're going to call them sigma bonds. We're going to get to them later. But notice that there's a combination of the sp3 and the 1s orbital, and actually this is what results in the tetrahedral geometry. So you should think of bonding. Yes, it's easy and nice to think of the lone pairs or as a bonding pair or just a bond like this. But in reality, you have something similar to this. This is the better model. This is much more practical, of course, if we use, if you remember this. It's much more practical and easier to draw. But no single chemist says that, yeah, those lines are representative. They are good representations on our scale, but the actual one would look more like the hybridized orbitals right here. Good. So where does the theory come from? Because this is all nice. This is all an important theory. I'm going to need you to be able to, of course, predict the hybridization. So really, really straightforward stuff. But let's look at the theory really quick, because I don't like to teach just something without explaining the theory. The theory goes like this. Well, if you think about carbon, we draw the electron configuration. It's 1s2, 2s2, and it's 2p2. And the 1s2 is up, down, 2s2 is up, down, and then the 2p2 is up, up. Okay. Now, think about it. Think about it. This tells us that we only have two, this is the key, unpaired electrons. That's what it says. They are unpaired electrons. If this is true, then how come you have carbon in methane with 4 bonds? Because if you think about it, in order for carbon to bond with hydrogen, it has to have 4 valence electrons. It has to have 4 unpaired electrons. Because, the H is going to bring its own electron. And then, of course, that's where we get the structure, etc. Right? So the question is, where do you get those 4 unpaired electrons? There's a violation right here. We can see there's a contradiction. Well, that's where chemists had to think of this valence bond theory, and it works very, very well. Here's what the theory says. It says, in order for you to get 4 unpaired electrons for carbon, it has to go through a 2-step process. So let's start with, we're only going to draw the valence orbitals. So you have the 2s and you have the 2p. And I'm going to use, again, different. Okay. The 1s, remember, is not, this is in the core shell, so it's not involved in bonding. So we're not showing it. It's there, but we're not showing it. So what has to happen is the first step is that it's a promotion of one electron from the s to the p orbital, from s to p. So what happens is the following. One of these electrons are going to be promoted. Does cost energy, because this is less energy than that one, but you promote that. And when you promote that, look what happens. Look, count how many unpaired electrons you have. 1, 2, 3, 4. 4 unpaired electrons. Good. However, we're not done yet. The reason why we're not done is because they're on different energies, so they have to be together. So that's where step 2 comes in. Step 2 says it's called hybridization. Basically, what you do is you take the S, as I showed you before, on the top right here, and now mix it with these 3p orbitals. So you take this box, mix it with that one, and then you make something new. You make new orbitals in the middle. Notice how the energy is in between. So you make 4 new orbitals. And now watch, they all have unpaired electrons. So hybridization, and these are sp3 orbitals, s and 3p's. So that's one of them. So that's sp3. So then you also have sp2. You also have sp, you have sp3d, and then sp3d2. So let's show you, as I showed you above, this is how when you mix them, you get these hybrid orbitals right here. The sp3 orbitals. If you take one s and you mix them with 2 p's, correspondingly, you will get sp2. But what I want to draw next to it is, notice how you used all the p orbitals in the sp3. So therefore, you have plus 0 unhybridized p orbitals. You used them all. You don't have any more. However, if you look at the second one, you only use 2 p orbitals. So you must have what? You must have 1 unhybridized. So here we're going to say plus 1 unhybridized p orbital. And then finally, think about it. And the last one, if you mixed an S and a P, then you must have, and then you made the SP, which they have, remember, look how this shapes are corresponding, trigonal, planar, and linear. Then you have 2 unhybridized p orbitals. Very well. What do I need you to do? I need you to be able to determine the hybridization. I need you to have, of course, a basic understanding of what we just did. And be able to, of course, reason throughout this. So let's begin. What is asked? How do I determine the hybridization? Well, here's how. In order for you to determine the hybridization, rather than going through, this step right here, although you still have to have a basic understanding of this theory, there's a quick method. We call that the steric method. And we did talk about the steric number method. So let's write down what the steric number is. A steric number is the sum of electron domains. And you have to remember what an electron domain is. So a single bond is one electron domain. ED, again, is an electron domain. A double bond is one electron domain. So please be aware of this common mistake. Some students think that since we have a double bond that we have two electron domains. No, think of it as a single bond is what? Two electrons. Think of it as a group of two electrons. A double bond is four electrons or four bonded, remember involved in electrons, and the ones that are involved in bonding. Think of them as a group of four electrons. It's still one group. And a triple is also one electron domain. And then finally, if you have a lone pair, it's still a domain. It's a group of electrons. Domain, you can swap the word domain with a group. So how do I use all of this? Well, if you have a steric number, Sn, by the way, is a steric number. If you have a steric number of 4, that would be sp3. S and 3 p's. If you have a steric number of 3, what do you think this is going to be? sp2. If you have a steric number of 2, that's sp. Now, they can go above 4. We're going to get to them in a second, but let's just apply this right away. Good. So I'm going to talk about molecules, but I'm going to show you the Lewis structures because by now you should be good at drawing Lewis structures. So if we have the Lewis structure of CH4, I know you just need the Lewis structure of CH4. So if you draw it, you get this. How do I determine the hybridization? The following way. Just go and find the steric number. So steric number Sn. Okay, here we go. This is a domain. A single bond is one domain. That's 2, that's 3, and that's 4. So 4, we said, if you forget, you just count, it's 1 S and 3 P, so that would be sp3. So therefore, the hybridization of carbon is sp3. If I have right here. Let's determine the hybridization on carbon first. So we got to find the steric number. How many electron domains are on carbon? Well, here's a domain. A single bond is a domain. Here's another domain. That's 2. And this double bond is 1 domain, the double bond. So you have a total of 3. So therefore, it's sp2. Okay. Oxygen, you can determine the hybridization on oxygen. And I'm going to use the color also blue for this, so you can see them. So I'm going to just erase these so we can. Okay. Here's a domain on oxygen. Here's a second domain, and that double bond is also a domain. So the steric number is 3. Also, oxygen has an sp2 hybridization. So this is on O, and this is on C. H, CN has this structure, H, C, and triple bonded to N. Okay, let's determine the hybridization on C. On C. Well, let's find the steric number. Here's 1, and the triple bond is also another domain, so that's 2. A triple bond, remember, is 1 domain. So here's 1 ED, and there's 1 ED. So that's a total of 2. And what did we say 2 correspond to? Here it is. 2 is sp. It's just an s and a p. Again, of course, we mean the hybrid orbitals. So therefore, you have sp. Okay. Let's do another one. So let's say we have P H3. So if you draw this, you know, P has 5. You have 3 H's, 1, 1, 1. That's a total of 8 valence. It's going to be a P and a lone pair with 3 hydrogens and a lone pair on it. So let's determine the hybridization. 1, 2, 3, and 4. So what did we say 4 correspond to? Look here, sp3. So sp3, just waiting on this. Again, do enough of these. Here's the formula. It's in front of you, the steric number. There's not much really to it. It's a miraculous way of getting the hybridization rather than going through the whole typical theory. Nevertheless, you still have to have an understanding of the theory. So sp3. Okay, so what about something that is, let's say, bigger than this? Well, last time we drew SF4, and SF4 came out with this structure. Very good. question. So let's determine the hybridization. So steric number. Here's 1, it's 2, it's 3, it's 4, and that's 5. Okay. So, so we're running into something now. Okay, what is 5? Can we say sp4? Think about it. Can you say sp4? The answer is no, it's impossible. The reason why is because you only have what? 3p orbitals. So where did the fourth one come from? So this is incorrect. So then what happens? Then how do we get the hybridization? Well, think about it. If you have an sp3, after the p is filled, what comes after the p? So you have sp, what comes next? D. So it would be sp3d. Remember what we said, that something like anything in the period 3 and beyond can take more than 8 because they have d orbitals. Okay? Say we have VRF5. Again, they have their lone pairs around them. Okay. If you were to draw the Lewis structure of this, we did this in the last lecture, so you can go back and review it. You would get, Br has 7 and F has 7. Together, all of this would be 4a2 valence electrons. There it is. So what is the hybridization? 1, 2, 3, 4, 5, and 6 is the steric number, 6 domains. So what do you think? sp3 takes care of 4, right? So then what comes after that? D, but is 1d enough? Then it's d2. And on and on and on and on and on. That is it with hybridization. So notice what I told you when we started this thematic unit, that if you don't have a good understanding of quantum mechanics, there will be gaps. And if by now you still don't understand why the S is only 1 and the P is 3, you go back to your quantum mechanics lecture and again review that. It has to do with the quantum numbers. So yeah, the D can go up to 5. So you can have sp3d5 if you have such a molecule. And then what do you think comes after that? Then you have the F orbitals that come after that. So again, a good understanding of that is expected. So I want you to go to this sheet right here. And if you have it in front of you, this is going to help you tremendously. So luckily, you can kill 2 birds with 1 stone if you find the geometry or the hybridization. If you find one, you can find the other. So here it is. The hybridization for the linear is sp, 2 electron domains. sp, that's the steric number. The hybridization for the second one, you have 3, that's sp2, 3 electron domains. The hybridization for the tetrahedral and its sisters here, when you have, of course, lone pairs, would be sp3, then sp3d, and then, of course, lastly is sp3, D2. So look what you can get. You can get the angle, the geometry, and the hybridization all right here. And again, if you are planning on taking organic chemistry, and I believe many of you will, it would be good to review this or take this with you, because this is going to help you tremendously there. You will use hybridization all the time in organic chemistry because it's all based on bonding. So let's go now to our next topic, which is pi and sigma bonds. So pi and sigma bonds, and let me move them down here. So pi and sigma bonds are essential. A good understanding of that is also essential for organic chemistry. So let's talk about pi and sigma bonds. So far, we have observed that the electron density covalent is concentrated in a line connected to nuclei or atoms. We've seen this before. So here, all we can do is just go back. Right here. Here it is connected. See the bonding that is happening between the H and the 1s and the sp3 on methane. Or you can just look at this. Here it is. It's in the line between these two nuclei. This overlap. That's what we're talking about. Well, that is a type of a bond that we call a sigma bond. So here it is. It's right here in front of you. This electron density in the overlap region right here, that's called a sigma bond. And it has this Greek letter. I mean, it's the letter called sigma in Greek letter, sigma. But however, so we've been talking about single bonds in general as, of course, they're sigma bonds. But there's another type of a bond that's called a pi bond. And it's the second type here. It says that results from the overlap between two p orbitals oriented perpendicularly to the sigma bond. So if you look here, these are p orbitals. They are perpendicular to the sigma bond. Well, those, I'm going to add this to them, those are unhybridized. Remember, I told you that when you do not take into account all of the p orbitals, that some will be left unhybridized. Well, guess what? They also have, okay, one electron. Each has one electron in them. And those electrons do not want to be alone. They need to form a bond. They need to pair. Those spins have to pair up and down. So what happens is a new bond occurs. It's called a pi bond over here. And there's going to be an interaction between these p orbitals above and below. It's not just on the top, it's above and below. You can think of this as this mushy, fuzzy electron density that is going above and below. It's not just, above at one time and below at, let's say, another time. It is both up, above and below. Remember, we don't know. That's the whole point of the uncertainty principle. So that's called the pi bond. And if you look here, here's a good picture. You see you have the hybridization, sp3, or sp2, I mean, and here's your sigma bond in the middle. But you also have unhybridized p orbitals. And notice the interaction between them. There's an overlap between them, and they become above and below, and those are called a pi bond. Okay, so what do I need to do? Well, how do I need to what do I need to do with the sigma and pi bond? All I need you to do, of course, still know the definitions. If I give you a picture, you should be able to tell what's a pi, what's a sigma bond. But this is the most important thing. You need to remember this. Also remember it for organic chemistry. If you have a single bond, that's called a sigma bond. Anything above the single bond, you add a pi bond. So if you have a double bond, now it's two, a sigma and a pi. If you have a triple bond, it's a sigma and 2 pi. So sigma is always 1. You can't have 2 sigma bonds in a bond. You can't have 3. You have to have 1. What increases is the pi bond. Good. So let's go back. Or we can just redraw them here. That's fine. So say, because we're going to do one culminating example here. Let's say I ask you, give me the number of sigma bonds and pi bonds in a certain molecule, and you have to draw it. So here's sigma, and here's pi. It's actually P in Greek. It's pronounced, not pi. But here we go. By definition, a single bond is only a sigma bond. So you have, here's a sigma, here's a sigma, here's a sigma, and there's a sigma. So you have 4. Okay. Do we have any pi bonds? Nope. We don't have any double bonds or triple bonds. So we have 0 pi bonds. Okay. We drawn this. Same thing. Sigma and pi. Okay. If you would like to figure it out, you can pause now. So sigma, yep, there's always 1 sigma. Here's 1. Here's 2. And there's a third one in there. So that's 3. Now I have a double bond here. Double means I have 1 pi bond. So therefore, I have 3 sigma and 1 pi bond. Want to figure this out? You can pause now. Okay, so there's always 1 sigma bond. Here it is. There's 1 in there too. Let me erase this so that. So that's 2. Okay, but I have a triple bond. Remember, a triple has 2 pi bonds in it. Right here. So therefore I have 2, sorry. 4 total, of course, but 2 pi and 2 sigma. Very well. That is it, really. Be able to just draw the structure and go with that step. Now we're going to do final here a question that is and expect something like this on a quiz or on an exam. So I'll give you a big organic structure right here, and you will have to answer a question like this. It says number 1 is place all missing lone pairs on appropriate atoms. Okay. All you have to remember is that anything that doesn't have the octet, you have to put lone pairs on them. So H only takes 2, so you'll never see electrons on lone pairs on it. Carbon has 4 bonds, so it's happy. But let's look at this Br right here. It looks like this Br only has one bond. So it needs 8. So therefore you put, again, this is nothing new. We've done this in Lewis structures. So that way you have 2, 4, 6, 8. This chlorine is not happy either. 2, 4, 6, 8. Just remember, halogens have to have 3 lone pairs around them. Okay, but let's look at this oxygen. It has only 2, 4. So it needs 2 lone pairs. This carbon is okay. This carbon is okay because it has 2, 4, and this double bond is 4 electrons. So you have 4, 6, 8. Same thing here. But this N is not happy. This N has 2, 4, 6. So how many lone pairs? 2 more. Otherwise, everything else is fine. This carbon has 8, that carbon has 8, etc. Okay, next question. A, what is the geometry of C1? So I'm going to label C1, C2, and C3. So here's C1, here's C2, and here's C3. I'm going to erase them when we work on okay, so the geometry. Remember, if you figure out the hybridization or the geometry, either or, one or the other, you'll figure out the other one. So I'm going to look at hybridization from what I did before and figure that out. So let me just maximize this a little bit so you can see it better. Okay. So here's my C1. C1 has 1, 2, 3, 4 domains. So that's a steric number of 4. If we have a steric number of 4, that would be sp3. Okay. What did we say associated, what geometry is associated with sp3? If we have 4 bonds. So it's going to be a tetrahedral. It's 4 bonds right here. 1, 2, 3, 4. Tetrahedral. What angle is that? 109.5. Okay. C2. 1 domain, 2 domains, 3 domains. So that's steric number of 3. And for 3, we know that stands for sp2. Okay, sp2. It's trigonal planar for 3 bonds. Remember, this is a lone pair. So therefore, you have trigonal planar, and the angle is 120. The angle is 120. Okay, so I'm just going to call it trigonal planar TP for space purposes, and then this is 120. Okay, hybridization. Of course, you're going to develop a pattern. You're going to see that if you have one double bond, that's going to be trigonal planar in sp2. If you have all single bonds, you're going to see it's an sp3. That's why develop patterns. Don't treat examples as distinct from each other. They are following a pattern. So in this case, you have one domain, two domains. So that must be steric number of 2, which is sp. And the angle associated with sp is linear, is 180, and that's linear. Okay, hybridization at O. One domain, two domains, 3 and 4 domains. So that's a steric number of 4. And 4 stands for sp3. The geometry, okay, well, I have 2 lone pairs and 2 bonds. 2 lone pairs and 2 bonds. You remember, you can use your axe method. Once again, all over again, is bent. And again, we're just going to say that's 109.5, but it should be less. It's about 104 actually. But for now, we're going to say again, just less than 109.5. Hybridization at N, right here. 1 domain, 2, 3, and 4. So that's sp3. sp3. sp3, we already did say actually, let's look. Here's sp3. We have 1 lone pair and 3 bonds. One lone pair and 3 bonds, so that's trigonal pyramidal. So I'm just going to call it, well, okay, trigonal pyramid. And the angle is less than 109.5. CL, 2, 3, 4. Right here. So that's going to be 4. So that's a hybridization of sp3. Now, for this, since you might be saying, okay, well, where is it? I don't see it in here. It would be actually linear, but it's not included here. But don't worry, I'm not going to ask you, but I just needed to be consistent in this example. So actually, this would be linear. And that would be 180. But I won't ask you about something that is not on here, but just to be consistent and finish this example for me. And finally, number of sigma and pi bonds. So what I'm going to need to do, I'm going to need to clean up as much as I can here, because I need to show you where are the sigma and the pi. What I would do for you, if I were you, for sigma and pi, is I would count all bonds. Or I would start with the pi bonds. They're easy to pick out. So for example, pi bonds, I'm going to start with this double bond. You know, this double bond has 1 pi bond. And this triple bond has 2 pi bonds. So that's 1 plus 2 is 3. There are no double or triple bonds in here, multiple bonds. Okay, so now for the single bonds and the sigma bonds, I'm just going to count all of them. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's a sigma bond in here. So we said that there's a sigma bond in there. There's also a sigma bond in there, and there's 1. Okay, so let's count from the beginning. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Not sure if I counted this one. 24, 25, 26. Okay, let's just do a recount. Got to do that sometimes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So that should be 25. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Yep. Okay, that is it. Thank you for watching.